Hello, everyone. My name is Zach Winkler. I'm an electrical engineering graduate student at NMSU. And over the past few months, I've been working on estimating body condition scores using depth images. General overview of what we're doing. We are using depth images to assess body condition score. To do this, we're using support vector machines, or SVMs, and convolutional neural networks, or CNNs. Eventually, our long-term goal for the system is to be able to operate it in the field for long periods of time autonomously. Some of the benefits to ranchers would be a general or a better consistency in body condition scores than people could provide. So two people might score the same cow differently, and we hope to minimize that variance. We want it to be cheap and easy to deploy so that ranchers are more likely to use this system. We want to make it as risk-free as possible. And since the results are being generated by computers, they can be saved quickly and reliably without any need for manually saving Excel documents and that sort of thing. Quick overview of the design process. Anytime you're dealing with machine learning, you need to know what sort of data you're going to use. And so the first step would be acquiring some of that data. In this case, it was taking depth images of criollo cattle at the Jornada, which we did back in October. Then once we have the data, we'll need to process it. So that includes segmenting the images, finding just the cattle so that we don't have any background or any fences or anything for that. Once we do that, we'll need to extract the features. These features are important because support vector machines cannot accept whole images as inputs. They need single dimension strings of numbers. And so we've divided these features into two categories, shape descriptors and texture descriptors. These shape descriptors are things like the hue moments, the kernel PCAs, and the Fourier descriptors. And these are important because they describe the outline of the shape. So in this case, the cow. A cow with really low body condition score would have a very angular outline. And a cow with a high body condition score would have a lot of fat. And so it would be very round and very smooth. And these features are describing them. We also have texture descriptors like the GLCM features. These describe things like texture. So think about rib patterns that are protruding, vertebrae that are showing, and it's giving the SVM a more complete picture of what the cow looks like. Once we have those features, we'll need to train the SVM and CNN, and we'll need to choose things like kernel parameters, and that sort of thing so that we get our best accuracy possible. Then we'll need to validate our model and make sure that it's scoring data that it's never seen correctly. And there might be multiple iterations of this process, but right now we are on the first model validation. This is a few pictures of our image acquisition setup. As the cow runs down this lane here, it'll trigger a proximity sensor. That sensor will tell the RFID scanner to scan the cow's ear tag and the camera to take the picture. And then eventually it will spit out a body condition score. This picture in the center is the camera enclosure. We have a huge heat sink on the side of it because it gets very hot inside. And then on the right, we have the internals of this enclosure. So we have the RFID scanner in red, the computation unit in green underneath, and the camera on the very right. This is another setup that we have at the Jornada. We have a very small camera attached to a second set of PVC pipes, and this is recording video to my laptop off screen. We're recording video because these cattle can move pretty fast sometimes, and we don't want to miss it in case the trip camera isn't dialed in all the way. And this is what we get in return from the camera. We get an RGB image on the left, and we get a depth image on the right. So we'll take those images, and we start with the original image on the left. We'll subtract things like fence posts, the ground, hands that might be touching it, anything that isn't the cow. And we end up with the segmented image that we then rotate and crop so that they're all relatively the same. Here are those features I was talking about earlier. These are describing shapes. So they're just to show you that we have decomposed this shape of the cow's hindquarters into strings of single dimension numbers. And these are all describing the shape of the cow. So we have the hue moments in the top left, the Fourier descriptors in the bottom left, and the kernel PCAs in the bottom right. So I've been talking about SVMs, or support vector machines, quite a lot. And so I thought it would be helpful to go through a small example to show how they work. So a support vector machine attempts to draw boundaries between classes, and these classes are represented by the features. So in this example, we have three classes, yellow, green, and purple. This SVM has attempted to draw boundaries between all of them, and it's done a pretty good job segmenting the purple from the others, but it struggled with the yellow and green. And so this would affect the accuracy of this SVM because we have yellow being classified as green because they're in the green area, and green as yellow because they're in the yellow area. And so we can improve our accuracy by using an SVM kernel. This transforms the original data into a more separable feature space, which is useful for nonlinear boundaries. So if we can't draw a straight line through the data like we can't in this other example with red and blue, we can use a kernel to transform it into a feature space where we can draw a more separable line or a more straight line, like in this example. So let's take a look at our data. This data has been scaled to have a mean of 0 and a variance of 1. And this graph represents the two greatest variances between the features for each cow. And this is just to show us how separable these classes are. It's not the be-all, end-all. It doesn't mean that these classes aren't separable. It's just to give us as people an intuitive way to check that. And so right here, they don't look very separable. And that's why we're using a kernel, so that we can kind of pull them apart and maybe we can draw some lines in between them once we do that. Here's a sample data set that we're using for our neural networks. Because we have so much data, we can use these data-hungry algorithms. And so we've transformed the data to better accentuate features that we know as people are useful for classifying cattle based on their body condition. So in the top left, we have the depth image. And in the top right, we've transformed that depth image into a high-pass filtered image. And this shows us things like the pelvis, the spine, and the shoulders. It highlights them because we know that those are important for body condition score. And then we've also traced this depth image to show the edges of it. Edges are very important for neural networks because just like us, they use edges to differentiate between objects. And we want to make sure that our network cues on those as much as possible when classifying these cattle. Then we've gone ahead and we've stacked all the images on top of each other to make this total image in the bottom right. So let's look at our performance. These are confusion matrices. They're not to confuse us, they're to show us where the models have been getting confused. And so we have our ground truth in the rows, and we have our predicted labels in the columns. And ideally, we would want a nice white stripe along the diagonal like we have in the center here for VGG16, which is one of our CNNs. And well, these are really, really good confusion matrices. They have really high accuracy. You know, we're getting 97% accuracy on one of them. I didn't think that they were very indicative of real life performance, and I'll tell you why. Normally, when we are using machine learning to classify objects, we take our whole data set and we shuffle it and we divide it into smaller data sets. So we'll have training, testing, and validation. And because we record a video, we might have images that are very, very similar to each other in the data set because we'll record 30 images a second to make a 1 second long video. And so one image that was taken right after another image will be so close together that they'll be almost the same. And so when we shuffle our data set and we divide it into multiple data sets, there could be some overlap between images. So it would be the equivalent of having a homework problem on your exam. You should know the answer to it already. And that's what these models are telling us, that they know the answers to the questions already. And so what I've gone ahead and done is I've, instead of withholding percentage of images, I withheld percentage of cattle. And that gives us a more realistic response of the model. And so when we go through these, they all have pretty much the same issue. They all have problems around class 4. So our SVM has a stripe at class 4, which means it's classifying everything as 4. VGG16 has its data, its guesses clustered around 4. It's guessing things as 4 a lot. And SqueezeNet, which is another CNN, has its results offset by 1 around class 4. And this could be caused by a couple issues, but I think that it's because of a data set imbalance. So if you think about your herd, you don't want extremes on the lower end of the body condition score spectrum. So we're not allowed to make very low body condition score cattle, so we're not going to have a lot of samples there. And having high body condition score cattle isn't always feasible outside of a feedlot, and especially out on the range. And so we have about 60% of our 55 cows as class 4 or very similar to class 4. And so our models are learning that since everything is 4, we can just guess 4 a lot and it will be reasonably accurate, which isn't what we want. And so some of the methods that we can use to get around that would be doing things like collecting more data. More data is almost always going to be good for these networks. And so some updates and current work on the project. We've gathered data in late October at the Jornada. We used about 4,700 images, about 55 cattle in total. And right now we're optimizing kernel parameters, we're fine-tuning the SVM and CNNs, and hopefully our future data gathering, which is hopefully in the next month or so, we'll have more data. So more cattle in the lower ends of the spectrum and better data overall. If you have any questions, I'm happy to answer them.